Hello, Luke. Welcome to Lesson 39. Today we're going to be talking about three separate things. We have the Trichotomy Axiom, Negated Inequalities, and Advanced Ratio Problems. So we have our work cut out for us today. So to begin with, let's talk about the Trichotomy Axiom. This is going to be a pretty simple one because it's actually something that we already know. We learned it in our last lesson. We are only now putting a name to it. So in our last lesson, we talked about comparing numbers. And we said if you take any two numbers, we'll just call them number 1 and number 2, okay? Two different numbers, or they might be the same, just any two numbers. There are only three possibilities that we can give them when we compare them. So we might say that n1 is equal to n2. That's one possibility. We might say that n1 is greater than n2. That's another possibility. And then finally, n1 may be smaller than n2. These are the only three possibilities between any two numbers that you might select. So if you think of a number in your head right now, and I think of a number in my head right now, we could say that your number is equal to my number. That would be pretty coincidental. Or your number might be greater than my number, or your number may be less than my number, but there isn't any other option. All right, there's no other option for those two numbers that we have selected. All right, now this sounds like it's pretty obvious, but actually in mathematics, this is a really cool observation, and it's something that helps us to solve certain problems later down the road. So we give it a very special name. Hey, it's important. Let's give it a name. And the name we give it is the Trichotomy Axiom. It's as simple as that. The Trichotomy Axiom. Okay? And it's appropriately named. An axiom in mathematics simply means a principle or a statement that we accept as true. So it's kind of a major rule in mathematics, or something that we firmly believe is true, and we use it to solve other problems. So that's what an axiom is. It's that principle that's founded in truth. Okay, trichotomy has that word tri in it here, or that syllable tri, and that's an indication of three. So it's kind of the three-part principle. Okay, and the three-part principle is indicating these three possibilities, okay, when we're comparing two numbers. That's why we call it the trichotomy axiom, okay? So there you go. There is the trichotomy axiom. Pretty straightforward. All right, now let's move on, and we're going to talk about negated inequalities. And we're actually going to use this trichotomy axiom here a little bit for this concept as well. So let's just throw some numbers down. Let's say I have x is greater than 4, right? We already know how to read that. We already know how to read x is less than 4, and we already know how to read, obviously, x is equal to 4. Now, in all three of these statements, and actually I'll throw one more in. How about x is greater than or equal to 4? And maybe we'll just throw one more, and x is less than or equal to 4. All right, these are a bunch of different ways that we can compare numbers. Now, this would be one way to do it. We can also go one step further and introduce one more symbol, and that is the slash. Okay, so if we have x is greater than 4, and then we draw a slash through this, okay, that would indicate that this inequality, greater than, is not true. Okay, it's not true. So the way we would read this is x is not greater than 4. Okay, x is not greater than 4. If I were to draw a slash through this one, it would read x is not less than 4. This one, x is not equal to 4. This one, x is not greater than or equal to a 4. And this one, x is not less than or equal to a 4. All right. So when we draw that slash through, it's just indicating that what's underneath the slash is not true. Okay, now looking at these, we can now actually take this one step further and try to understand what this would mean. And that is, we can write it in a different way. So let's think about this. If this is saying x is not greater than 4, well, then what is x if it's not greater than 4? Well, that brings us back to the trichotomy axiom. X can only be one of three things when we're comparing it to the 4. It can be equal, it can be greater, or it can be less than. Here we're saying that it's not greater than. So it's not this one. Okay? If it's not greater than 4, it could be equal to 4, or it could be less than 4. Those are the only other two options here. So another way to write this would be x is, if it's not greater than 4, it could be less than or equal to a 4. Okay? Do you see how that is? I have to include both the less than or the equals because by saying it's not greater than 4, it leaves me with these other two possibilities. All right, let's try the next one. So this one is saying x is not less than 4. Well, then how could we rewrite that without the slash? Well, we could say x is, if it's not less than, then it's not this one, but it could be either of the other two, right? And therefore, it could be greater than or equal to a 4. Okay? Now, this next one here, x is not equal to 4. Well, this one we're not really going to be dealing with right now, but just so that you can kind of understand the concept here, x is not equal to a 4. Well, what would that mean? Well, that would mean it eliminates this possibility. X isn't equal to a 4, but it could be greater than 4 or it could be less than 4, right? So we would say that x, oops, let me get my pen here. X is greater than 4, or x is less than 4. Okay? It could be either one of those. X is greater than 4 or x is less than 4. And I could have written that as x is greater than 4 or x is less than 4, if that makes a little more sense to you. Here I just have my greater than or less than signs going in the same direction. So I had to flip the x to the other side. But anyway, I digress. So the idea here is that if it's not equal to a 4, it's got to be less than a 4, or greater than a 4, or less than a 4. Okay? I should probably get rid of these now because that looks like greater than or equal to. Okay. All right. Now that one, I don't think they're going to give this one to you in any of your seat work right now. I think they're working primarily with inequalities. But that's how that one would go down. You kind of have a dual answer there. Could be either one. All right? All right, moving down to the next one. So this is x is not greater than or equal to a 4. Now that's an interesting one because it eliminates two possibilities, doesn't it? It's not greater than, and it's also not equal to. So that means it eliminates this one and this one. And that leaves us with just the less than 4. So therefore, we could rewrite this as x has to be less than 4. Okay? And then this one, x is not less than or equal to 4. Again, we're eliminating two possibilities here. We're eliminating the less than, and then we're also eliminating the equal sign. That gives us just the greater. So the result is x has to be greater than 4. Okay? So this slash that we've been talking about, we call that the negation of the inequality or the equal sign. It's the negation mark. And the negation means that you add a not in front of it when you're reading. X is not greater than 4. X is not less than 4. So that negation sign, that slash, just think of it as the word not. All right? That is what we're talking about when we talk about negated inequalities. So let's just take that one step further and make sure that we can actually graph these. All right. So if I give you this inequality, let's say x is not less than 3. And I asked you to graph all the possibilities for x, all the possible solutions for x. Well, remember, that would mean that we're going to have to draw our number line. So we draw our number line, and then we're going to insert on our number line maybe a 0 here, a 1, a 2, and maybe a 3, and we'll go up to maybe a 4. Okay? And then we're saying, looking at this inequality, what does it mean? X is not less than 3. And whenever we have that negation slash, it's usually easiest to first write this in a way that makes a little more sense to us. Our brains don't work too well when we have to incorporate it into it a negative. We work a lot better with positives. So if we have a not less than 3, well, let's talk about what that means that it is. So if it's not less than 3, then it has to be what? Greater or equal to a 3. Don't forget, it could be either one of those. This only eliminates the less than, nothing else. So now we have kind of something that's maybe a little more understandable to us. This is basically what you've been doing before in the previous lesson. X has to be greater than or equal to a 3. So we first, well, we'll go to a red here. We'll first put our dot. In this case, it's going to be a solid dot on the 3 because x could be equal to a 3. And then x is going to be greater than a 3. So if it's greater than a 3, then that would mean that we have to be going this direction on the number line. Okay? So that is how we would graph it. Let's try another one. What about x? Whoa, that's not going to work. Let's go with x is not greater or equal to a 2. All right, so once again, we draw our number line, and we'll put maybe a 0 here, a 1 here, a 2 here, and then over here we'll throw a couple negatives, -1, -2, -3, and so forth. All right, so x is not greater or equal to a 2. What would that mean in kind of more of a common language here? If x is not greater than and it's also not equal to a 2, then it has to be less than a 2. That's the only thing left over from the trichotomy axiom. So now looking at that, x is less than 2. We can put our mark on 2. In this case, it's going to be what? A hollow circle, right? Because it's not equal to a 2. That's not a possibility. It has to be less than a 2. So we can't solidly mark the 2. Let's then draw our line. So it has to be less than a 2. So we're going to go off for infinity in that direction. Okay? Okay, very good. So that should make sense to you. Let's move on to our last piece of the puzzle today, and that is looking at more complicated ratio problems. So first off, let's just take this first ratio problem and just do it. So we have something to compare the new ones to. This is exactly the same as the ones that you learned yesterday. So let's just do it real quickly here. The ratio of red marbles to green ones is 3 to 5. If there are 9 red marbles, how many green ones are there? Well, the first question we would ask for remember we have kind of our ratio side of the problem here. This is our ratio side. Okay, and what is the ratio? What's being compared here? Well, up to this point, we've been saying, oh, well, red marbles to green marbles, so we're comparing red to green, right? The red to the green, all right? And we can actually even fill those in. The red to the green is 3 to 5. All right, so that's our ratio right there. And then remember, we have our big equal sign here, and on the other side, we have kind of what's in the problem. What did we call it last time? The reality side. So, you know, what in reality are we dealing with here? And in this case, we're dealing with 9 red marbles. So because we put the red on the top over here, we have to put the red on the top over here. 9 red marbles. And then how many green ones are there? Well, we don't know, so we're going to use a G for that, right? And we have 9 over G. Okay, so maybe if I just rewrite this over here without my boxes, I have 3/5 is the ratio equals 9 over g, and that is my proportion. Remember, two ratios on either side of an equal sign. We can cross multiply. 3 times g is 3g. 5 times 9 is 45. We can solve for g by dividing by 3 on both sides, and we end up with g is equal to 15. All right, so there are 15 green marbles. All right, so that is just a review problem. Now let's move on to some new material here and look at how these problems can become a little bit more complicated. So let's read the next one here and see if we can discern the difference between the second problem and the first problem. So the ratio of red marbles to blue ones is 2 to 5. If there are 21 marbles total, how many are red? All right, so the whole idea here is, up to this point, our very first question has been, what's the ratio, right? What are we comparing? And in this case, we might, draw our box here again and remember that this is our ratio side to the proportion, and we're trying to figure out what ratio to put in here. And we might say, well, what are we comparing? Well, we're comparing red to blue, right? We're comparing red to blue, and that comparison is the ratio 2 to 5. And we might just say, okay, there's my 2 to 5, red to blue. Okay, but now we're going to take this one step further and recognize that given any ratio, such as this one, we can actually pull out two other ratios as well. Now remember, a ratio is just a comparison. So what else could we compare in this first sentence of our story problem? What else could we compare? We've already compared the red to the blue. Now we could compare the blue to the red, but that would be a little trivial. We're still comparing the same two things, so that doesn't really count. But what else could we compare? How about comparing the number of red marbles to the total number of marbles in the ratio? So we have 2 red ones for every 5 blue ones. We could also say then that they were having 2 red ones to every 7 total, right? 2 plus 5 is 7. So another ratio here would be 2 red marbles for every 7 total marbles. All right, just take a second and think about that. Think about how that's working. We could compare red to blue, or we could compare red to the total number in the ratio. Now, one side note on this, be careful. When I say you're comparing the red to the total, don't get confused and think I'm referring to this total over here, where they say there are 21 marbles total. Remember, we're kind of breaking this up into 2 parts. We have the ratio part, and then we have what we've been calling the reality part over here. And this over here is actually in the reality part of the problem. That's how many marbles we see in total in front of us right now. The ratio is different. The ratio is just kind of dividing all of our marbles up into groups and realizing that for every 2 of the red, we're having 5 of the blue. So it's kind of 2 separate parts of the problem here. Don't mix them. All right, so this first part is just dealing with the ratios. The second part is dealing with the reality. What do we have in front of us? Okay, so when I say total, what we need to remember is we're adding up the total in the ratio, 5 plus 2 in this case. So we have 2 red out of the total 7 marbles in the ratio. Very important. All right, so that's a second ratio. Can we come up with a third ratio? Well, actually we can. What about comparing the blue to the total? We compared the red to the total. Why not compare the blue? That's another comparison. The ratio for that would be, well, we have 5 blue marbles in a total of 7, so it would be 5 over 7. Okay? And there we have it. So when they give us a ratio, we need to recognize that you can actually pull out 3 different ratios from that single ratio that they give us. Now, why is this important? It's important because this next part, the reality part, that's going to dictate to us which one of these ratios we need to use in our ratio box to solve the problem correctly. All right. So the first step, the textbook, the Saxon textbook actually recommends that the very first thing that you do is write down all the ratios that you can pull from the problem given the information that they give you. And I think that's a really good practice, especially at the beginning here when we're just learning how to do these problems. So this is the first step right here. Write down all of the ratios. All right. Step number 2 is then deciding which one of these ratios should we put into our ratio box in our proportion right here. And to decide that, we need to look at the second part of our problem and look at what they're asking us. What do they want to know? All right. And if we look at the second part, it says if there are 21 marbles total, how many are red? So they're giving us one thing. They're giving us the total right here. And then they're asking us how many are red. All right, so we have a total and we have red. So what we need to do then is look over at our list of ratios and decide which one of these is using total and red. And if we look at our variables here, we have red over blue, red over total, and blue over total. The only one that's using the red and the total is this middle one, right? That's the only one that's using the red and the total. So that is going to be the ratio that we're going to use. So we'll set that 2/7 in our ratio box here. Okay. Now we can look at what's in reality. In reality, they're telling us that there are 21 marbles total. So we're going to have our ratio here. We need to decide where this 21 is going to go. The 21 is a total. And if we remember our ratio, the total was on the bottom. So we need to put the total on the bottom over here as well. We need to make sure that these stay in line. Totals are with totals. In this case, red is with red. And we know that the red is what we're looking for. We leave that as a variable. We don't know what it is. But we have red on top, totals on bottom. Okay? Now we are at that point where we just need to solve the proportion. And to do that, we cross cancel. So we take the 7 times it by the r, or multiply it by the r, we get 7r. And then we can take the 2 times the 21 and get 42. Then we can divide by 7 on both sides. And we end up with r is equal to 6. So the number of red is 6, given the total 21. And that actually makes it really easy to discover how many are blue, doesn't it? Because if we have 21 total, well, and we have 6 red, and the only other color is blue, well, wouldn't that mean we have 15 blue? Just kind of a tidbit there. 15 blue and 6 red. Okay? Very good. Let's try a couple of these and see how you do. So let's do this one together, and then the next one I want you to try to tackle on your own, given what we've learned. So, the ratio of whales to dolphins was 2:9. If there were 44 animals total, how many are dolphins? Okay, well, let's think about this. So, let's start with step number 1, which is to discover all of our ratios. So let's put those over here. So what do we have for ratios? Well, we have whales to dolphins. We'll go W over D. Okay. Whales to dolphins, and they tell us what that is. It's 2:9. So that's pretty easy, pretty straightforward. Now, what's another one? Let's think about totals here. So what if we were to go whales to total? Well, we have 2 whales, and the total is 9 plus 2. So we have a total of 11 in our ratio, 2 plus 9. So it would be 2 over 11. We could also do dolphins and compare that with the total. Well, the number of dolphins is 9 out of the 11, so 9/11. All right, so there we have our 3 ratios. Now we get to decide which one we're going to use. So we have our equal sign here for our proportion. Let's look at what they're telling us here. If there are 44 animals total, how many are dolphins? Okay, so we're looking at a total here, and we're looking at dolphins. here, a T and a D. So we need a ratio that has a T and a D. In this case, it's just this last one. So we're going to use the ratio 9 over 11. Okay, equals, well, what does it equal? We have 44 animals total. That's what they told us. So our total is where? It's on the bottom. So we need to make sure that our total here is also on the bottom. And then on the top, we have our D for dolphins. All right, so now we have 11 times D is going to be 11D. And we have 9 times 44. Well, let's do that off to the side here. 36, 39. 396. Oh, my. All right. Now we can divide both sides by 11. And we get D is equal to 396 divided by 11 is going to be 36. So we end up with the number of dolphins equaling 36 when we have a grand total of 44 whales. Which again, if we wanted to take it one step further, we could say that if there's 36 dolphins and there's 44 animals total, that's going to give us, what, 8 whales? Okay, just as a side note. All right, let's go down to the next problem here. Why don't you look at this one and try to do it yourself first, and then we'll do it together. All right, so let's try this one out. The ratio of children to adults at the party was 5 to 2. If there were 42 people total at the party, how many were children? All right, well, let's write our ratios out. So the first ratio we have is the ratio children to adults. We'll just say C over A is equal to, and they tell us that it's 5 over 2. That one's an easy one. Now let's get those totals out of the way. We have children to total. What's the total? Well, 5 plus 2 is 7. So it's a total of 7. And the total number of children out of that 7 is children to adults, 5 over 7. And then if we go from there to adults over total, the total number of adults is 2 out of the total again, which is 7. So there we have our 3 ratios. Now, which one should we use? Well, what are they looking for? They're looking for, they give us a 42 people total, and how many were children? So we're looking for a total and a children. And what do we have? Total and children would be the middle one here. So that's the one we'll use. So we have 5 sevens equals, what do they give us in reality? We have 42 people total, and again, the total is on the bottom, so we put 42 on the bottom. And then on the top, we have children. We don't know yet. And now we can multiply this out. Cross multiply. 7 times C is 7C. 5 times 42, we'll just throw that off to the side here so we don't make a silly mistake in our head, is 210. Now we can divide these out. And we end up with C is equal to 210 divided by 7, which is, of course, 30. So the number of children is 30 children when we have, well, how many adults? 12 adults. And I just got that by knowing there's 42 total. 30 of them are children, so 42 minus 30 is 12. All right, but what they want to know is how many children. So this is our official answer to the problem. All right, very good. So hopefully that makes sense to you. I think we will actually stop there, and you can work these out in your seat work, and we will continue tomorrow.